All right, today we're going to deconstruct one of the unsung heroes of our electrical world, the low-voltage power circuit breaker. Now, I know, it doesn't sound super glamorous, but trust me, without these things, our modern lives would just grind to a halt. Their job is absolutely critical.
To really wrap your head around what we're dealing with, just think about this question for a second. How in the world do you stop an electrical current of 200,000 amps? That is more than enough power to literally vaporize solid steel in an instant. It's that kind of terrifying, destructive force that these devices are built to control.
Just let that number sit there for a moment. 200 kiloamperes. That's the raw, untamed energy that these breakers can stop dead in their tracks. We're talking about the short-circuit breaking capacity of the absolute powerhouse we're taking apart today.
You know, that brings us to the name low voltage, which is actually a little bit misleading. Because while these devices do operate in systems under 1,000 volts, the sheer amount of current they have to manage is anything but low. They are true, bona fide powerhouses.
So what is it exactly? Well, at its core, it's a protective device. It's designed for electrical systems running under 1,000 volts, and it really has two main jobs. First, it has to handle incredibly high continuous currents. We're talking over 6,000 amps just cruising through it. But more importantly, its job is to instantly, and I mean instantly, shut down a catastrophic electrical fault.
This table here shows a really fascinating trade-off in electrical engineering. Think of it like a river, okay? High-voltage systems are like a narrow, super-fast river. You've got high pressure, but maybe not a huge amount of water flowing at any one time. Low-voltage systems, they're the exact opposite. They're like a huge, wide, slow-moving river. Low pressure, but a massive volume of water. So to deliver the same amount of power with lower pressure, or voltage, you need an absolutely immense volume of current. And that is why these breakers have to be built like fortresses.
Okay, so we get what they do, but how did they do it? Let's start our tour right on the front panel. This is the main interface for any operator who has to work with this thing.
So the first thing you're probably going to notice is the trip unit. And this thing, this is the brains of the whole operation. It's constantly feeling the pulse of the circuit, and if it detects anything dangerous, any kind of fault, it makes the instantaneous decision to trip. It protects everything downstream. And these things are getting crazy advanced. Some of the modern ones even have touchscreens.
Next up, you've got your hands-on controls. Super simple, super reliable push buttons. You've got a green one to close the circuit, a red one to open it. Right next to them are these mechanical indicators that give you an at-a-glance status update. Is the breaker open or closed? Is that big spring inside charged up or discharged? It's simple, it's effective, and it's actually required by safety standards.
And you can't miss this big black handle, right? That's the manual charging handle. See, these breakers use a crazy powerful internal spring to operate, and that spring needs to be charged up with potential energy. Usually a little electric motor does that automatically, but this handle is your crucial manual backup. If you lose control power, you can still walk up, crank this handle, and get the breaker working.
And one last little thing on the front here is the operation counter. Now its job sounds simple, but it's totally vital. It just counts. Every single time the breaker opens and closes, it clicks up by 1. This gives you a running logbook, which is absolutely essential for scheduling maintenance and just understanding the life this device has lived.
Okay, so we've seen the controls on the outside, but where does the incredible raw force to open and close that circuit actually come from? Let's go under the hood and look at the real heart of the breaker, the operating mechanism.
It all comes down to this, the stored energy mechanism. This is the muscle. So first, a massive spring gets wound up, charged with a ton of potential energy. Think of winding up a giant, powerful clock. That's done by the motor, or that manual handle we just saw. Then, the second the trip unit gives the command, all of that stored energy is released in a flash. This unleashes this immense force that is needed to slam the electrical contacts open or closed with unbelievable speed.
Now let's pull back a bit. Beyond the internal workings, these breakers basically come in two main flavors. And believe me, the choice between them has huge practical implications. So on one hand, you've got the fixed type. And it's exactly what it sounds like. It's permanently bolted into the electrical panel, and its connections are all hardwired in place. But on the other hand, you've got the withdrawable type, which is really cleverly designed to just slide in and out of the panel on its own little chassis, using a kind of plug-in system for all its power connections.
Honestly, this is the perfect way to think about it. The withdrawable breaker is basically a giant industrial-strength USB device. You can plug it in when you need it, and you can just unplug it to swap it out. It's brilliant.
So, fixed, withdrawable, who cares, right? Why does this matter so much? Well, it matters a lot.
because the choice between these two designs has a direct and really significant impact on uptime, maintenance, and, you guessed it, money. Let's just walk through a nightmare scenario, a critical fault. With a fixed breaker, you have to power down the entire panel, send a technician in to manually unbolt the unit, disconnect everything, install a new one, reconnect all that wiring, and then re-energize the whole system. We're talking hours of downtime. But with a withdrawable breaker, you use a special tool to rack out the faulty unit, which safely disconnects and pulls it out. You slide in a spare and you rack it back in. Power can be back on in minutes.
So what's the bottom line here? It's pretty simple, really. This one architectural choice has massive consequences. For something like a data center or a hospital, a few hours of downtime can mean millions of dollars in losses, or even worse, it could put lives at risk. The withdrawable design is an elegant and powerful solution to that very, very expensive problem.
So we've seen how these incredible devices handle unbelievable power and why their physical design is so critical. But all this leads to a final thought for the future. As our hunger for power just keeps growing and our electrical grids get smarter and more complex, how are these essential protectors going to have to evolve to keep up and keep us safe?